If mathematics is the queen of sciences, as the great mathematician Carl Friedrich Gauss christened it in the 19th century, then physics is king. From the mid-17th century to the end of the 19th, Newton's law of gravitation, his three laws of motion, and his differential calculus described with apparent perfection the mechanical motion of objects in our world and the solar system. In 1864, 200 years after Newton, the Scottish physicist James Clerk Maxwell formulated the compact and elegant differential equations that described with similarly astounding precision the propagation of light, X-rays, and radio waves. Maxwell's equations showed that electricity and magnetism, formerly separate phenomena, were part of the same unified electromagnetic field. We cannot simply look at the world around us and deduce Newton's laws or Maxwell's equations. Data on its own does not speak. These equations were triumphs of the mind, abstracted from the world in some miraculous confluence of hard thinking and deep intuition. Their success confirmed that pure thought and beautiful mathematics have the power to discover the most profound laws of the universe. At the start of the 20th century, the pace accelerated. Einstein, pondering the conflicts between the Newtonian and Maxwellian views of the world, proposed his theory of special relativity that amended Newton's mechanics and made them consistent with Maxwell's equations. 15 years later, Einstein trumped Newton again with his proposal of the general theory. It corrected the law of gravitation and described gravity as a large-scale wave in space and time. At almost the same time, Bohr, Schrödinger, and Heisenberg, with help from the ever-prodigious Einstein, developed the quantum mechanical theory of the small-scale behavior of molecules, atoms, and subatomic particles. It was Einstein who perfected this mental approach to discovering the laws of the universe. His method wasn't based on observation or empiricism. He tried to perceive and then enunciate the very principles that constrained the way things should work. In a 1918 speech on the principles of research given in honor of Max Planck, the discoverer of the quantum, Einstein captured the magus-like appeal of trying to see through a glass darkly when he said, "There is no logical path to these laws. Only intuition, resting on a sympathetic understanding of experience, can reach them." What is the purpose behind the search for scientific laws in any field? Clearly, it's divination, foretelling the future and controlling it. Most of the modern technologies we enjoy rely on, detest, or fear cell phones, electric power grids, CAT scans, and nuclear weapons, for example, have been developed by using the basic principles of quantum mechanics, electromagnetic theory, and relativity, all of which were discovered by cerebration. The classic tools of 20th century divination have indeed been those of physics. More recently, physicists have begun to employ the same tools in finance. For the past 20 years, throughout Wall Street and the City of London, in most major and many minor financial institutions, small groups of ex-physicists and applied mathematicians have tried to apply their skills to securities markets. Formerly called rocket scientists by those who mistakenly thought that rocketry was the most advanced branch of science, they are now commonly called quants. Quants and their cohorts practice financial engineering, an awkward neologism coined to describe the jumble of activities that would better be termed quantitative finance. The subject is an interdisciplinary mix of physics-inspired models, mathematical techniques, and computer science, all aimed at the valuation of financial securities. The best quantitative finance brings real insight into the relation between value and uncertainty, and it approaches the quality of real science. The worst is a pseudo-scientific hodgepodge of complex mathematics used with obscure justification.